ideas. I hope you all enjoyed dinner yesterday evening. Now it's time to go back to science. And as all of you know, IDA is very much an interdisciplinary conference where people meet from different directions. So on the first day, the keynote speaker, they've seen a perspective on analyzing ranked data from a statistician. Yesterday, we've seen from a database theory perspective how we can do DNA computing, and today we're just going in a very different direction where we're going to see some astronomy and then how to use citizen science for that. So it's a great pleasure today for me to introduce to you Professor Chris Lintott from University of Oxford, where he's also a research fellow at New College. So Chris started studying physics a long time ago, and well, he already knew that he wanted to do astronomy, and well, that's what he did. So he studied the formation and evolution of galaxies, but this turned out to be a pretty hard problem also. That's where the citizen science came in later. Apart from that, he's also a very passionate advocate of increasing the public understanding of science, and he's spent quite some time and effort also on that. So you may know him from Sky at Night, a very long-running BBC program where he's co-presenter. He also wrote a book called Ben, which is quite popular and which gives more or less a complete overview of the history of the universe. And well, then there is this Zooniverse project where he does citizen science. And citizen science is the idea that, okay, these tasks are so hard for humans, for computers, let's involve humans in that scientific process, and let's see how we can use that information to improve the results. And this started with what it's called the Galaxy Zoo, where the goal is to discover new galaxies. And actually, people have discovered new galaxies there. And well, we are data scientists, so data analysts. How do we formalize this problem? Well, we have a set of images of stars or galaxies, and then it's a classification task. So, is this a new galaxy, or is it just a star or some other artifact in the image? And well, by having hundreds and thousands of people doing these classification tasks, and it's actually possible to do this. That's very cool, and this was very successful. I got some awards also in 2011 and 2014 this year from the Royal Society, American Astronomical Society. So some nice awards there, and this was expanded then to the Zooniverse, where there's a large number of projects. And of course, well, I went there, I wanted to try it, right? So I saw that there's over 1.2 million people now who volunteer to go there and contribute to science. So I think that's already very nice on itself. And some tasks are very hard. And if you go to the Worm Watch lab, you can see pictures of or videos of worms who move around, and you have to mark when these worms lay an egg. I can tell you this is very difficult at first. At some point maybe you get the hang of it, but it's very difficult to get to do this accurately. Other tasks are easier. There's Penguin Watch, where you just have to mark all the penguins and their eggs. Well, if there's 60 penguins, this is not actually so hard to do. There's also the whale song, Whale FM, where you can classify songs of whales, to classify and group cluster families of whales. So if you're doing research and you are stuck at some point, you don't know what to do, go to Zooniverse, try it out. It's fun to do, and maybe it's even also inspiring for your own research. In any case, you're contributing to science in a different way. That's it for now. So today, Chris will talk about how to merge these machine and human efforts, and what challenges are there also maybe for us as data analysts. Chris, please.
Thank you. It's a pleasure to be here. I really enjoyed myself getting to know you through the talks and also at the banquet. I think it's wonderful that when you have a speaker
first on after the conference banquet, which is always difficult, that the introducing person gives their talk for them. So we can move now to questions. No, but before we do that, let me give you the detailed version of what you've just heard, and I will try and end with some thoughts about where we need to be to cope with a situation that I think afflicts most of modern science. Then this picture is a good representation, I think, of how many of us feel about our data. We've got very good at building machines that can provide us with information about the universe or about whichever bit of the world we want to study, but we haven't really dealt with the consequences of those machines. And I know for this audience that's not a message that I need to labour. In some ways, we're much better as modern scientists in collecting information than we ever are at using it. And this is, as you'll know, a fairly recent phenomenon. I was doing some writing on a different topic, and I was looking at the data of astronomy from 100 years ago. And this is what astronomical data looked like at the end of the 19th century. So this is a nearby galaxy. It's the Whirlpool galaxy with a few individual stars in it. This was an absolutely critical observation because the resolution of stars in one of these spiral structures told people that they were, in fact, distant galaxies, and the scale of the universe expanded because of this observation. But it's a sketch. It's made by somebody dressed formally, probably on top of a ladder with a pen and pencil. And this was how science got done and how we studied galaxies not much more than 100 years ago. These days, of course, we don't sketch, we build machines. This is one of my favorites. This is the Sloan Digital Sky Survey. It's at an observatory in New Mexico. And Sloan, for 8 years, did nothing but map the sky. On most nights, it would be pointed at a particular angle, and they would allow the sky to turn over it. And if you do that, then a galaxy or a star crosses the field of view of this camera. You can just think of this as a giant camera. It'll take a couple of minutes for the star or galaxy to cross that camera's field of view. And in that time, the telescope would take images in 5 different wave bands, 5 different colors. And on the best nights, they went back and measured the distance to 1 million of those galaxies. So Sloan was really the first survey that gave us a detailed structure of our local bit of the universe. And so I can show you that now. So we're going to start on the Milky Way, on our own galaxy, which has 100 billion stars or so in it. And we'll go outwards through the Sloan. I've only got about half the galaxies in this video, for which I apologise, but I'll add the others at some point. We'll start on the Milky Way and we'll go outwards through the universe. Do you think we can lose the lights on the screen, maybe? It's a bit bright. But if not, even you can see, first of all, that there's lots of space between the galaxies, that space is in fact empty. But that each one of these systems with hundreds of billions of stars has a particular position. And when you get out to when you get out to this sort of scale, what you can see is that there is structure, even on this sort of large universal scale. So the universe is lumpy. There are places with lots of galaxies, the big superclusters linked by filaments, and there are places where the universe is rather empty of matter. And the net result is this honeycomb structure that you can see in a minute will stop and it will rotate, and you'll get a real sense of the almost fractal structure that we see in the universe. This was a surprise. So astronomers had always believed that when you got to these scales, things would be pretty smooth. The fact it looks like a bow tie, by the way, is just a consequence of the fact we haven't finished mapping yet. So those gaps are the equivalents of here be dragons, if you like, on the old maps. They're the bits that haven't been filled in. But the structure is real. And the game that we play in trying to understand that structure is to build our own model universes like this one. This is a simulation, the results of a simulation run in a large supercomputer. And you can roll your dice, play the MCMC game, and put yourself on a galaxy in here, and you can pretend that you've got a Sloan Digital Sky Survey and observe this universe, and then you can compare the real and the simulated universes. And to do that, you need a metric, of course. You need to choose a way of comparing the two, And in general, we stick to some simple comparisons. So this, for example, is what we'd call the mass function. So this is just, we're only dealing with the stellar mass here. So the points are observations drawn from the Sloan Digital Sky Survey for the most part. You've got the mass, the Milky Way would be in the middle here. And it's just a density of galaxies that have that mass. And the green and red lines are fits from different simulations. You're not astronomers, so I need to tell you this is an excellent fit. We're very pleased with this. In particular, we're pleased because most of the weight in the function is actually on that knee, that point where the two power laws change. But it's clear that something odd is going on at low masses. So we're getting the number of small galaxies wrong. Apparently you can either over or underestimate, depending on how you like. And over on the other side, we're getting the number of large galaxies wrong. So there's this problem, even with this simple metric, in recreating the universe that we see. And one solution to that is, one can go and add more parameters to the simulations. You can create all sorts of feedback processes that try and fix this problem. But really, to resolve it, what we need is a better view of the universe. We need to not just treat each galaxy in the survey as a point with a mass and a position, but as an individual. And if you look at a random selection of galaxies, these are all from the local part of the Sloan survey, but this is a random selection, you can see that there's more information here than just a point particle. So each of these galaxies has a shape. We call it morphology usually because that makes us sound more scientific. But it's really just the shape. And the shape is, if you like, the integrated dynamical history of the galaxy. So it tells you about whether the galaxy has interacted with its surroundings. It tells you about whether it's merged with other galaxies. And it tells you whether and when it's formed stars. And so if you can look at each of these images and record the shape of a galaxy, you suddenly have a much more sophisticated means of interrogating the data than just saying there's a galaxy here with a mass of 10 to the 11 solar masses. And astronomers have known this since the 30s, and we've relied on classifying shapes since then. In the beginning, professors would classify shapes and write books with their own atlas of galaxies, and everyone would have their own classification scheme. You could have a happy conference arguing about who to believe. By the time we get to the 80s and we have tens of thousands of galaxies, people are relying on students to do the classifications. There's less interest in arguing about the classification schemes, but as long as the students can look at them, that's fine. But as Sloan was being developed, and other big surveys, it was already apparent that we were going to have to do something about this. And my old supervisor, Ofer Lahav, who's now at University College London, wrote this fabulous paper in Science in '95. This is like an astronomer discovers the need for data mining. If you read it, you guys would enjoy it. It's only a few pages, and it says things like, we will need to use statistical approaches to analyze our data. But he says classifying very large data sets is obviously beyond the capability of a single person. Therefore, we need a new approach. And between '95 and about 2007, the field explored the obvious set of machine learning techniques that you might use. There were lots of work done with neural nets to try and solve the galaxy classification problem, and the work done was pretty good. People managed to do the basic classifications of galaxies to an accuracy of 90%, something like that, which is pretty good, but not good enough for the research that we wanted to do. We wanted a better than 99% accuracy in even simple classifications. And so when I arrived in Oxford in 2006, we discussed this problem. We tried again to get a student to classify 1 million galaxies. The student's name was Kevin. And Kevin did 50,000 galaxies before telling me where to stick the rest of them. Those weren't quite the words he used, but it was pretty close. And so in sort of desperation, we decided to ask the public for help. Not the first time this had been done, but a new enough idea at the time. And so this is the original Galaxy Zoo. It looks every inch of the 7-year-old website it is, back when frames were cool. And Galaxy Zoo was designed really to do the simplest thing that would still be useful. So you get a picture of a galaxy. We ask you whether it's an elliptical, a big ball of stars, or whether it's a spiral. If it's a spiral, we want to know which way the arms are going, and I'll say more about that in a second. And then we say it's a merger or a star, and that was it. 6 buttons, you got a galaxy, you clicked a button, you got a galaxy, you clicked another button. And this was, I assumed, going to take a while. So I thought that this would operate with me giving talks to local groups of amateur astronomers. Maybe 50 people would go and classify 50 galaxies each. And we worked out that in 5 years we could get through the 1 million galaxies. But it turns out that it's rather hard to succeed quietly on the internet. Things either fail on the web or they succeed grandly. And Galaxy Zoo was getting 70,000 classifications an hour within a couple of hours of going online. And we haven't quite continued at that pace, but we're on hundreds of millions of classifications. And so that meant that we could take multiple classifications of each galaxy, which gave us immense power in understanding, not just being able to assign a classification, but getting a sense of how reliable each classification was. There's an obvious difference between a galaxy where 10 out of 10 people say it's a spiral, and a galaxy where 6 out of 10 people say it's a spiral. So we got this very powerful data set. Galaxy Zoo has gone from strength to strength. In particular, we now ask a much more detailed set of questions. So there's now a decision tree, so we ask whether there's a bulge or a bar at the center of the galaxy. If there are spiral arms, we want to know how many there are. We look for the odder things that come up every so often in an effort to get much more information about these galaxies. Of course, project design is important. People generally give us what we ask for, but as an example, this was a button that was used in one of I think from the second iteration of Galaxy Zoo. And we were trying to capture the idea of a galaxy that had maybe had a close encounter with a neighbor, and so hadn't been completely disrupted, but it had been warped or disturbed in some way. And so we invented this nice little logo for that and said, okay, this is a disturbed galaxy, and here are the systems for which our volunteers return. So we have the largest collection of pixel dropouts. These are places where the camera has just not recorded one pixel as the galaxy is tracked across the image. And it's hard to argue with the volunteers. You know, this is a perfectly reasonable response to that button. And from this, we learnt to test things properly. But on the whole, the system works very well. And the classifications we get from Galaxy Zoo, even without any sophisticated weighting, are the equal of those done by professional astronomers. So we outperform small groups of experts, and the data has been used in all sorts of ways. I don't really want to take advantage of your slightly hungover states and turn this into a talk about astrophysics, but there are a couple of nice results that I think illustrate different parts of the power of this sort of distributed human computation. One is, to go back to that thing I mentioned, that we asked about the direction of spiral arms. So obviously there are differences between these two galaxies. So one has spiral arms going in a clockwise direction, one going in an anti-clockwise direction. And this is sort of interesting because in most cases the direction of the arms tells you how the galaxy is rotating. So the one at the top really is rotating clockwise, the one on the bottom really is rotating anti-clockwise. And just before Galaxy Zoo launched, there was a guy called Michael Longo from the University of Michigan, I think, who is a retired particle physicist who's got interested in cosmology. And he looked at 3,000 galaxies from Sloan, 3,000 spiral galaxies, and he said he saw more anti-clockwise galaxies than there were clockwise. So the universe had some sort of preferred direction of galaxy rotation. This is a result that would overturn most of cosmology. So for starters, it would depend on your position in the universe. You could travel to the other side of the Sloan survey and look back, and you'd see more clockwise rather than anti-clockwise galaxies. So this breaks something called the cosmological principle, which says that our observations of the large-scale universe shouldn't depend on our position within it. And to explain it, you end up, at least in a bar, talking about magnetic fields threading the universe, or geometries based on the donuts and that sort of thing. And whenever a theorist reaches for an explanation based on warping the universe's geometry, it's a sign of desperation. So we didn't believe this result. 3,000 galaxies is not really enough. The statistics was slightly wobbly in the paper. And we thought it would be easy enough to check. And pretty soon we had 200,000 spiral galaxies, a proper run at the statistics. And to 7 sigma, we found more anti-clockwise galaxies than clockwise galaxies. So we replicated this apparently crazy result. And I was all for writing the Nature paper there and then. After all, Nature papers don't have to be right. But calmer heads prevailed, and we just flipped all of the images and started showing people the mirror image of each galaxy. And if the result had been true, or if the result had been cosmological, we should then have expected more clockwise than anti-clockwise galaxies. And actually the opposite happened. We still saw more reports of anti-clockwise galaxies. It's easier, for some reason, to see spiral arms when they look like the top example and not the bottom example. And this is a very subtle effect, but because we had so many people and so many galaxies, we were able to pick this out. And the best explanation I've heard is linked to something called the ballerina illusion. So this is audience participation time. So if you imagine looking down on this dancer, how many of you see her going clockwise? Quite, that's most people. Anyone see her going anti-clockwise? Counterclockwise if you're American, a few people. Has anyone seen her switch? Yeah, if you can bear it, if you want to see a switch, if you wave your head from side to side, doesn't make much difference, but it amuses me. So, so first of all, it's strange that we don't have a consensus, right? That there are people in this room who disagree about which way this apparently obvious figure is rotating. And what's happening is that your brain is making a decision about how to interpret this two-dimensional object in three-dimensional space. And there are a couple of solutions to that, and you can flip between them. And we're seeing similar effects, we think, with the spiral galaxies. What we're seeing is people perceiving them as coming into or out of the page and occasionally missing what's going on. And the bias of anti-clockwise over clockwise is to do with issues of right brain and left brain dominance. So it's a fascinating psychological study. We could adjust for it. Once we'd measured this bias, we could take it out and we could get on with doing astrophysics with the results. Another thing that I think is important is, well, this brings me to Brian May. Brian is, for those who don't know him, he's a postdoc in astrophysics at Imperial College in London. Having taken 30 years off to pursue a music career, he came back around the time that we were doing this stuff. He came back to astrophysics and spent a year finishing his thesis. Luckily, his topic was so boring that no one had touched it in the 30 years he was off being a rock star. Slightly facetious, but it was on dust in the solar system. It's about as exciting as it sounds. Anyway, so Brian was interested in Galaxy Zoo. He wrote a nice blog post and told all of the Queen fans in the world that they should go and do Galaxy Zoo, creating an enduring bias in the musical tastes of our volunteers. One of the people who followed Brian's instructions was this lady. This is Honey van Arkel, a Dutch school teacher. She has the same guitar as Brian. And Honey was the first person to see this thing. Now, normally I get away with my pronunciation of this, but could somebody in the room who speaks Dutch please tell me, present to the room the name as written in the top left of this image, please? Thank you. Good. So I will just point at you when I need to say Vorwerp, because I'm told I don't get anywhere near it. But nonetheless, and what does it mean? Yeah, exactly. So it's object. We thought it was a technical term when she turned up on our forums and started using it. And we've managed to get it into the literature as the official name of this object, so, which is rather nice. We've also got the plural. So Vorwerpen has been published as well. And Vorwerpjes, which is the diminutive, is also now in the scientific literature. So this is very pleasing. Anyway, I'm not going on about this for linguistic reasons. My point is that if you're a neural network and you've been trained to classify galaxies as either spiral or elliptical, and you see this image, you might, if you're a particularly good neural network, tell me that there is a spiral galaxy there. It's actually a warped disk. There's something odd going on with a dust lane across the front of the galaxy, but you can see a couple of spiral arms in what's probably the effect of a recent merger. If you're human, you don't really care about the galaxy because you want to know why there's an evil version of Kermit the Frog sitting directly underneath. And so the point is that by paying individual attention to all of these galaxies, as well as getting our classifications done, we get serendipitous discoveries, even on the scale of surveys with millions of images. And more to the point, these serendipitous discoveries come with advocates, right? We got interested in this because Honey turned up on the forum and said, "What's this? You know, I found this thing. What is it?" And she was quite loud about it. And so the scientists creaked into action and tried to chase this thing. And it was great fun. It became the kind of thing that I thought astronomers did when I was a kid. When I was a kid, I thought astronomers found strange objects, pointed telescopes at them, and then argued about what they were, instead of messing about with statistics and big surveys. And that's exactly what happened here. The first thing we discovered was that the Voorwerp is at the same distance as the galaxy. And so that means that it's big, right? It's a galaxy-sized gas cloud. It's hot. The gas is about 50,000 Kelvin. But there are no stars in it. And so the question immediately becomes, well, how is this thing being heated to 50,000 Kelvin? It's not a very complicated detective story. You know, there's a culprit on the scene. And we thought, okay, well, what must be happening is that galaxy at the top looks like it's been disturbed. That means that material tends to flow down onto the black hole, which exists at the center of all large galaxies. And when that happens, you get what's called an AGN, an active galactic nucleus. The material that's heading for the black hole gets very hot. It's a very efficient way of converting matter to light. And in particular, you can also get jets of material expelled at right angles to the disk at about 99% of the speed of light. And so if you imagine a jet coming out at a right angle from the galaxy, it may well have hit this Voorwerp and heated it up. So it's a nice example of activity in a nearby galaxy exciting a cloud. And the way to check this was to go and look at this galaxy in the X-ray. So if you look at this with an X-ray telescope and that black hole is actively feeding, you get to see the hot gas that's spiraling down. And so we did that, and we found absolutely nothing. So this is not an AGN. And so our best guess is that for once in astronomy, we've caught something that's in the process of changing. So the Voorwerp, the distance between the center of the galaxy and the edge of the Voorwerp is about 50,000 light years, which means that the view we get of the center of this galaxy from the Voorwerp is 50,000 years behind the view we get by looking at the galaxy directly. So there's a dogleg. It's what we call a light echo. And so 50,000 years ago, this must have been an actively feeding galaxy. In fact, it would have been the nearest such system. And it's just shut down. And we knew that this happened because we see the statistics of the populations of these things change. But we didn't know you could observe it in individual systems. And we've managed to do that because a single classifier engaged in a different task turned around and said, there's a weird thing here. And I think a lot of the power of citizen science is that combination of a routine classification task and then a sudden diversion into serendipitous discovery. And I'll come back to that at the end. The other thing that we didn't expect to happen when we built Galaxy Zoo was that I started getting called by other scientists. I got phone calls from sheepish chemists and ecologists overwhelmed by data and all sorts of other people saying, look, you know your people who look at galaxies, do you think they can help me with my data as well? Because as I said at the beginning, this problem of having collected more data than you know what to do with is rather common. And so there's also the obvious realization that once you've built software to run a decent website that can present this for galaxies, you've also solved the problem for other images as well. And so we expanded Galaxy Zoo pretty quickly into what's called the Zooniverse. The Zooniverse now hosts 25 separate projects. You heard about a couple of them earlier. And so, for example, we've done it's Halloween, Bat Detective, which is listening to recordings of bats and distinguishing them from the background noise. Cyclone Center is a really difficult but intriguing project to do historical analysis of hurricane photos. We've done more astronomy. The Andromeda project was a project to look for star clusters in our neighboring galaxy. I say was because the crowd got through the million or so classifications we needed in a couple of days. So that project didn't last very long. So it went, and Snapshot Serengeti, which it was our first attempt to attack the growing number of camera trap projects in ecology. where instead of sending a PhD student to the field to follow lions around, you send a PhD student to the field to carpet a study area in hundreds of cameras. But you've still only got one student to look at the results from hundreds of cameras. And so these have been great fun to develop. We've tended to pick projects that do something different because we think of them as independent experiments. So each one is a project in its own right that will produce science, but they're also natural experiments in what works for scientific crowdsourcing. And so you can start to think about spaces like this. This is the average time on site from our analytics, the number of visitors. Sorry, the numbers have got dropped, and this is this morning. And so you can see there's a sort of main sequence where most of our projects lie. There are some failing projects. Bat Detective, for example, and Whale FM are our two audio projects. And so we've learned, we think that audio is much harder than video, because you're much harder than images, because you're asking for more of somebody's attention. Operation War Diary is very topical. It's transcribing World War I logs. It's a humanities project. But on the whole, we begin to be able to predict how many classifications we're going to get. And there are, of course, other commonalities between these projects as well. So, for example, this is the distribution of effort for a project called Old Weather. So each box on this diagram is a single user. And the colours are completely arbitrary. They're just there to distinguish. And what you can see here is a pattern that we see across many of our projects. So lots of the effort comes from a small handful of deeply committed users, people on the left here. However, somewhere between a third and a half of the effort comes from the people who only visit the site once or twice, maybe 3 times at most. And I think this is something, from a design point of view, we have to worry about. We have to build sites that are engaging to people who are going to hang around forever. We can't do without the right side of this diagram. But I also need a site where people can be useful very quickly. It's no good building a project where you require 10 hours of experience to produce anything useful, because otherwise we lose the entire other side of the diagram. And this is something that drives our analysis of the data as well. You know, you can't, if half of your classifications are coming from people who you know very little about, it puts a severe restriction on the amount of user weighting that you can do. Or at least you can't build a system that depends heavily on lots of information about each user. It constrains the amount of training data I can put through people. Or I can put people through, both. You know, because otherwise they won't be useful. And so I think this sort of pattern, which we see as common, provides general principles behind all of these things. It also drives you, I think, to be efficient. And so you're all doing very well, by the way. You're all very awake. So you get some animated GIFs of animals as a reward. So these are real captures from Snapshot Serengeti. So Snapshot Serengeti, these cameras trigger 3 times in response to motion. And the task is species identification. So for 3 of these, I suspect the species is obvious to you all. You classify the one in the bottom left as human, by the way. The top left, I don't know how much you know about different types of gazelle, but it's easily taught. And Snapshot goes through and looks for 50 different species. It's part of a study of how massive carnivores coexist in this interesting environment. But because we want people to be useful very quickly, there's a large pressure on us to retire images, to decide that images are done as soon as we have a consensus. And so you can start inventing rules for consensus. And so what we used originally for Snapshot was this. So if the first classifications are blank, then we decide that there's a blank classification. I should have put the animals on this slide as well. I'm sorry, that was a very brief interlude of looking at warthogs. It turns out that these cameras, 70% of the data returned by these cameras are mostly images of grass, because what happens is the grass in front of the cameras grows and heats up, and then when it's a windy and hot day, the cameras, which are infrared and motion triggered, pick up the waving grass and then continually take pictures of it until their SD card is full. And so we have to be aggressive at getting the blank ones. Then, you know, and obviously if the first 5 are blank, then we get rid of it. If 10 at any point are blank, then it goes. If 10 users say there are 2 zebra here, then we return that. Otherwise, we stop at 25. So that's reasonable. One can improve on that. So we've just had a paper accepted to a conference where we looked at other aggregation algorithms. So to give you an idea, here's one that works well. So we've gone down to 3 classifications only being blank. So we've saved people from looking at a lot of empty Serengeti fields. Otherwise, after 10, then we have this weighting equation where we're using user weights. So the W here is the combination of the total positive identifications and the total negative identifications. This is per species, given by each user, divided by the, we have some gold standard training data, so we can do false positives and false negatives. And the only tweak that isn't utterly standard here really is that it's much easier to say that there's nothing in the image. And so we downweight the influence of being able to do that on a user's classification. Almost anyone can say there's nothing there, distinguishing a Thompson's gazelle from an elk or something. An elk? Thompson's from, I've forgotten the other name of the gazelle. Distinguishing types of gazelles is rather difficult. There's one that the ecologists call cheetah burgers, but I can't remember its scientific name. Never mind. The point is this works very well, and we get better than 96% accuracy when compared to expert classifiers. So that's very nice, and the Serengeti results have been hugely helpful. We've also proved to my satisfaction that people like looking at pictures of animals on the internet, which is probably not the most interesting research finding. But it did lead to this. So camera traps are common. We have a bunch of penguinologists in Oxford who go to the Antarctic and place cameras that take images every 5 minutes. So this is a typical image. They're interested in monitoring the health and behavior of the penguin populations. Until now, these colonies have been visited a couple of times a year, and you get snapshots of what's going on, or occasionally you can monitor penguins by satellite. You can't see individual penguins, but you can get a sense of where they are. And so, going back to my theme of generalization, one can, just as we generalize the sort of decision rules about what should be retired, we can generalize the clustering algorithms one uses on a marking project. So this is a piece of code called Milkman, which delivers data to the scientists. So each of these is an identified penguin. It's images like this that remind me that the original name for this project was Penguin Hunters, that we dropped that one. And you can see the individual classifications. And you can see immediately that this is from the early days of the well, you see immediately that our clustering algorithm is working pretty well. It even picks out these 2 things. But it's clear we're overclassifying. We have too many classifications on each penguin, and so we've been able to change the site so that we get fewer penguins. Yes, you see, you don't need 20 classifications to note that there's a penguin there. But then we can spit out the location of the penguins and deliver this to the scientists. And that's proved to be important. One of the biggest problems of this project has been my assumption that all scientists work in the same way as astronomers. This turns out not to be true. For my data, for Galaxy Zoo, I wanted the raw data. I want to know that this user has classified this image and said this. That this user has classified this image and said this. And then I want to do the consensus, because I'm the expert and I'm going to publish my scientific paper based on the results of that consensus. It turns out that for most of our scientists, that step is as big a problem as dealing with the data in the first place. So some of our projects, we took 1 million images that people didn't have time to look at and turned it into a 10 million line database that they have no idea how to read. And that problem of going from simple classification to consensus is a hard one. And so we've now generalized it for our projects. And so when people build projects with us, we also do that step for us. But it's taken us a long while to realize that we had to do that. And speaking of generalization, we've been rebuilding the code as well so that we can build projects in a programmatic way. If you look at the site at the minute, most of the projects have their own sort of flavor and they're bespoke developments, although there's a shared code base underneath them. From next year, you'll be able to go to Zooniverse, upload data, upload images, and launch a project as easily as you can use WordPress to launch a blog. So we're going to open up the platform so that people, research groups without web developers, can use it. So the Penguin Watch you've already seen. The bottom right is our next project, which is Higgs hunters. So we're going to look at LHC data. It seems a ridiculous thing to be doing human computation with. I'll tell you more over coffee. Higgs hunters will almost certainly fail to find anything interesting, but if it succeeds, then there are Nobel Prizes, because it's looking for the weird and the unusual within the Large Hadron Collider dataset. The only difference between these projects is 6 lines of code. And so we've got to a point where we can put these projects up extremely quickly. And we expect to expand from 20 to 200 or 2,000 projects in the next year or so. And there's no evidence yet that we're running out of people. Every time we launch a new project, we get more volunteers and the time spent on existing projects goes up. The other driver that's pushing us in different directions is this need to be efficient. Because so far, I've allowed people to go and classify and then looked at the results afterwards. And even when I've applied user weightings, I've done that in retrospect. Taken a large database of classifications and then gone through and decided who to trust. And for future projects, that's not going to be good enough. So we've started to experiment with being more sophisticated. I want to tell you about a project called Space Warps. Space Warps looks, we're back to galaxies, we've had the animal bit now. Space Warps looks at distant galaxies, and in particular galaxies whose light has been lensed by passage near a nearby galaxy. So Einstein taught us that gravity bends space, and that means that light traveling near a massive object will bend. And so you get these, I don't know if you can see it because of the lighting, but there's this is a nearby galaxy, and then this blue arc here is a distant galaxy which we have an imperfect image of. Think of this as a natural telescope. So Space Warps is interesting, but it's interesting mainly because we put in simulated distant galaxies. And so, and incorporated user feedback. So the volunteers got to find these things, and they were told, we don't want them thinking they've discovered a galaxy when it's one of ours, so we gave them a simulated lens, and then we tell them whether they got it. And similarly, we have false negatives in here. So we have images we know are blank, and we'll give feedback as well. So that's a good user experience, but it also allows us to track people's performance. And so, for example, this is 50 randomly selected people from the database. On the x-axis, you've got the probability that they say there's a lensed galaxy there when there is one. And on the y-axis, the probability that they say there isn't one when there isn't one. And so you have people divided in the top right into astute classifiers, the people who know what they're doing. In the bottom right, you've got people who are obtuse, or wrong, as we normally say. Of course, this won't be a surprise to you, but if you have a classification from somebody who you know is always wrong, that's just as valuable as a classification from somebody who is right all the time. You may want to apply this principle in life more generally. And we also have optimists and pessimists. So you can think about people who always think there's something there and people who always think there's nothing there. And so we can calculate the useful information provided by each of these people and think about the distribution of not just their classifications, but of useful information. And so we look at that as a whole. Ignore the orange and blue here. We ran Space Warps in a couple of phases. Just stick to the blue. And this is the distribution of what the team call contribution. So this is just the number of classifications. And you can see that 1% of the users do a ridiculous amount of work. 10% of the users do 99.9% of the work. This is a very steep distribution. And this is typical, by the way, of crowdsourcing projects. It's not just us. But if I plot not the contribution, but what the team calls skill, and the skill in each classification is the expected information from that classifier given a random image. So it sort of takes away the luck. Some people see images where they can contribute a lot, some where they see, by chance, see images where they can't contribute much because we already know the answer. So this is sort of a measure of how much knowledge you have to contribute to the community. You can see it's a much flatter distribution. It's still skewed towards a small function of users, but there is a lot of skill out amongst the users who don't do many classifications. You can look at that in more detail. If you look at the left column here, the left column is, on the x-axis you have the amount of effort, the amount of classifications. This is made by a bunch of astronomers, so these are all log-log plots. We find our data looks better that way. And then the second one down is X-skill, which is what I've just shown you. And you can see what I just said, which is that although there are people in the top right, they're the experienced classifiers who have a lot of skill. There are also people in the top left, people who have a lot of skill but haven't yet done many classifications. And if you look at the bottom, what we have there is the information. So this is the actual information contributed. So this is, how much information did you give me about that image that I've just shown you, added up over time. You get this nice flat distribution. So people, as they add more effort, they add more information to the project, but it is this nice broad distribution. So there is untapped effort that we can get at in there. If we can turn those people in the bottom left who are doing a few classifications but are actually providing useful information, we can identify them, we can get much more out of our classifications. And we started to look at that in a variety of ways. How long have I got left, by the way, about 5 minutes? 10 minutes, okay. I was going to talk about supernovae, but we won't. Once you have that information, you can look at what you would do with task assignment. So now I'm measuring people's ability as I go. I can think about, instead of a system that serves up random classifications, I can think about saying, okay, you're good at the faint galaxies, so you get this one, and you're good at the bright ones, so you get this one, and so on. And there's a whole pile of papers building up. This is one by Tammy Waterhouse from Google, looking at Galaxy Zoo. And this is sort of the response curve for accuracy with number of judgments. And the blue line, so the red is random assignment, and blue is some optimized scheduling that takes into account the information we have on the volunteers. And whenever people do this, it's quite easy to outperform random assignment for a large proportion, for a large number of classifiers. What's interesting is that we see again and again and again a small number of judgments per contributor. In other words, for projects in which a large number of people are only doing a few things, you're better off not even trying to optimize. And random assignment is good when you don't know much about your crowd. And so I think one of the open problems for us is, when do you switch? At what point do you go from, I don't know anything about you, you're just getting some random stuff, to, okay, now I've learned about you, here is the new stuff. Anyway, assuming we can solve that, I want to note in passing that as well as assigning tasks to different people, it's easy to add robots into this mix. If I'm measuring the performance of a classifier, and I'm assigning tasks based on that performance, I've built a system that can incorporate human and machine classifiers. It's easy. They're all the same to me in some sense. This is the point of the talk where people start looking at me quizzically. But at least in this very specific sense, there's no need to distinguish between the performance of automated and human classifiers. We can just make decisions about who should see what based on the characteristics of the image and our prior knowledge of it. And I think the future of this stuff is a hybrid system where almost all of the data is characterized by machines, but when conditions change and they need new training sets, we can quickly bring on a whole load of human classifiers. Or when objects are strange, maybe the Vorwerp, maybe you have a machine whose job it is to say, is there an extra object in this image? And you pass those images to humans, and you get this dynamic back and forth between the two. The problem is that if you're a machine learning person, you stop there and you think you've solved this problem. The problem is that our volunteers are indeed human, and they have behavior that would be very strange in a machine learning system. So this is, all you need to know to understand this graph is that having the blue, this is an accuracy, I don't have time to describe this project, but the blue line being along the top vertex is good performance. And this is a human classifier who is, as you can see, slightly inconsistent to begin with, and then fine, and then changes their mind about something. So maybe they got drunk, maybe they passed, this was on a Friday evening, or maybe they passed their login to somebody else, or more likely, I think, especially because it goes back, they changed their mind about what they were supposed to be doing. Something they saw made them think, oh, that question means something different. And so we have a very sudden change in classifier performance. This is hard to take into account. It's not that common, but ideally you'd want to detect that as it happened. And so you begin to create questions which the engineers struggle with. From a performance point of view, doing detailed calculations with large numbers of classifications coming in becomes very difficult. And so your task assignment could go horribly awry if this happens and you don't know that somebody has just got much worse. So there's this trade-off between being clever and being safe. You know, the more sophisticated our system is in terms of measuring performance and assigning tasks, the more likely we are after the fact to find that we've got a whole bunch of images that haven't been properly classified because this has changed and we hadn't noticed. The other problem with humans, this talk takes me to some strange places. The other problem with humans is particularly volunteers on the Zooniverse that doesn't exist in the vast literature on how to assign tasks in Mechanical Turk, Amazon's paid system, is that we have to worry about whether people are going to stay with us. So let's say I build a system that gives you perfectly the galaxy images that you're best suited to classify. We do a little bit of training, and then you get assigned your role is to look at mergers or fake galaxies or distant galaxies or nearby galaxies. And from an efficiency point of view, I feed you that diet of things you're good at classifying. It's exactly what you'd do with an ensemble of imperfect machine classifiers. In our case, we've probably just broken our project. Because what we've just done is remove all variety and fun from this task, and we turned it into work, right? And people do these projects because they're fun. They do these projects because they want to make a contribution to science. But on any given time, they're making a decision to do this and not check Facebook. And so if I treat people as machines, they will leave. Again, another rule you can use elsewhere in your life. And so these, for example, this is a project called the Milky Way project that looked at star-forming regions in our galaxy. And they're sort of beautiful. If you saw these two images in the first 5 images you were given, then on average, volunteers did well over 100 more classifications. If your first 5 images included these, on average, users did another 20. So we have to optimize for user interest as well as for user ability, which means you've got to detect motivation. And this is a hard problem, and it's not trivial. So in Snapshot Serengeti, for example, you'd think that the way to keep people on the site is to show one of the really stunning warthog photos, or any of the ones that I had up early on, right? You show people your best images, and then they hang around. Actually, we see the opposite. If people see a good image early, their expectations are raised, and then they're disappointed by everything else. Whereas if you show people an unremitting diet of just grass, and then a zebra in the distance, the zebra is really exciting, and people will stay on. And so we're beginning to be able to pick these patterns out of data. What we do with them, we don't know. I want to finish by just talking about one other source of data that we've begun to think about in this context. I don't have time to talk about the astrophysics, but all of ours, this is a project called Planet Hunters, in which people look at graphs for fun. But all of our projects have, almost all of our projects have a discussion environment. And we built our own discussion environment to be sort of object-oriented. So people talk about the thing that they've just seen. And so every comment, which can be quite detailed, this is a user doing his own analysis of a potential planet that he's found. Every comment is tied in the database to the objects that people are talking about. So I know not only that this user saw this image and classified it using the interfaces being a gazelle, I know that this user was then motivated to go and say something about it, and I know what they said. And so we've begun to think about using this vast set of comments to detect expertise. So you could think about detecting the kind of language that people use, and using that as a marker for how expert they are, and using that to influence either the user weighting or the task assignment. You can also think of this as discovering, we think we can use this to discover what people are interested in. If every time I see a zebra I bother to go and say something, then I've probably got some interest in zebras, and maybe we could up the zebra count. And so we have this interplay between a classification system and a discussion. And we do see changes. There's a project called Seafloor Explorer. When Seafloor Explorer, it looks at images taken by a robotic submarine off the coast of the US. It's a fisheries health assessment. And in the first week on the project's forum, these were 10 of the most common words used. That makes sense. Seafloor Explorer has a small but dedicated community who've mostly stayed together. It's one of the projects that hasn't had a subsequent boost So it's the same people still there a year later. Here are the 10 of the most common words used now, and I don't know what lots of these mean. So we have evidence for learning, which at the minute we're not acting on. And so we can tie these data sets together. And we need to do all of this. This isn't just me getting excited by a data problem or me trying to complicate things for fun and in order to get grant money, although it is fun and we do need grant money. I want to go back to this image that I started with, this nightmare of the robot, the machine running amok and scattering humans every which way. My version of this nightmare looks like this. This thing is the Large Synoptic Survey Telescope. It's as big as the biggest telescopes in the world today. It has an 8.4 meter mirror. Construction is underway. Here is the top of a mountain being blasted so that this thing will sit there. It's going to come online in 2018. Take a few years for science to flow after that. All its data is going to be streamed live, so anyone in the world has access to it. Just the images in low res are 30 terabytes a night. Or to put it another way, if you subscribe to an alert service that told you about anything that had changed in the sky, you'd get about 250,000 alerts a night with decent filtering. And we have to sort through those and decide what's worth following up within about 20 minutes of a change occurring. And most of them will be boring, and most of them will be sorted by machines. But my bet is that the really interesting stuff will need a human to stop and say, hang on, there's something weird going on here. And so everything I've been doing about task assignment, hybrid classification systems, serendipitous discovery, all comes together to try and deal with the consequences of the machines that we're making now. In other words, we've learned nothing from past experience, and we're still building instruments that are running way ahead of our ability to cope with the data. And that's not just in astronomy, it's everywhere. So I hope that was interesting. If you wish to spend some of your copious spare time on Zooniverse, you'll be very welcome. There are all sorts of projects. We have data coming out of our ears on user behavior and classification, and I would be delighted to share it with anyone. And if you ever meet anyone who could get some research done but just needs 1 million people to help out, we'd love to hear from them as well. Thank you very much.
Fantastic talk, thanks. And actually I have a ton of questions, but if I may, I'll just ask 2.
Sure.
First of all, as far as I was aware, we already found the Higgs boson. So what are the Higgs hunters hunting for?
So, not my field,
Okay.
but we found a Higgs boson, right? So we found something that seems to behave in a Higgs boson-like way. Understanding exactly what type of Higgs boson it is means finding all the different ways it decays. And what's exciting about the CERN project is that you probably know this, but most of the data at CERN never hits our hard drive. Right? There are a series of automated triggers that decide what's worth saving. And so something like 99.99% of data at the OHC is thrown away within a second of being collected. What we're doing is they save a random sample, and what we're doing is we're inspecting that for anything unusual. And the idea being that we're a sanity check on the set of triggers that we put in. If you go and find a random particle physics theorist, and you give them a beer, by the end of the beer they'll have invented 6 other things that are worth looking for that aren't in the trigger set. Yeah. And so that's the plan. That's why it'll probably discover nothing, because the triggers are probably right. But if we discover anything, it's hugely exciting. It's also, I mean, what's interesting about it, I'm not sure that it will work. Right, not just in the sense of discovery, but it's not clear to me. Our volunteers say they're motivated by wanting to take part in scientific discovery. It's not clear to me how they'll view those odds, right? Whether it's enough for them to do something that's potentially high reward but low health, and that's one of the reasons we're doing it. We want to test that point in parameter systems. Second question. Yes. All the answers will be this long.
Well, the system when you start talking about robots being part of it sort of reminded me about the server where I play Go. Usually human players, but the system encourages people to program their automatic player, and they get a special icon, but otherwise they're equivalent to the rest. Are you encouraging people to plug in their own software?
We're just beginning.
we've operated before now by, we just share data with machine learning researchers. We're building, in the rebuild of the platform, there'll be an API with a live stream of classifications, and that will also accept recommendations. So I hope we'll end up collaborating with a bunch of robots in that sense. But we haven't done so formally yet.
You said you were willing to share data on the use, but do you have specific questions? Because data doesn't mean very much to you. Are there questions that you would like help with?
Yeah, I have
I think that the main question I have is we need to find efficient means of task assignment. So given my current status of knowledge on this image and my current state of knowledge on this set of users, what should I do next? And I think we've done the simple stuff, like the back of the envelope stuff, and I think that there are quite a few people working on ridiculously complicated stuff. You know, full Bayesian, dynamic Bayesian analysis of everything that takes 10 hours to run, which is fine after the fact, but utterly useless in a live environment. And so top of my list is a more sophisticated approach to that problem that can actually be calculated on the fly. That's one example. In general, you know, I think I'm beginning to get a sense of what this community can do. But if people have ideas or thoughts about how this might mesh, then you know, I think the best thing to do is have a chat and a coffee today, and then we can see if there's a match. We will build projects that if there are characteristics of projects that would be interesting in the space that you're working, we can find projects that match those. If it would be interesting to have a project with a particularly complex interaction, or a project where everyone is forced to say something as well as classify, we can do that stuff. The truth is, I don't know your field well enough to list the 6 major research areas that fit. Zooniverse has been the 7 years of building it have been 7 years of slow discovery of other people I should have talked to earlier, and this conference is fitting exactly in that.
Other questions?
they want to go and look at intestinal worms.
Well, maybe ask something about motivation. So are you using these standard gamification techniques like leaderboards, badges, stuff like that?
Yeah, no, definitely and deliberately not in most cases. So, I'll talk on this. So, in a couple of projects we did, and we found that for the simple stuff, you know, you get a badge every 25, you have a rank and so on. That does more harm than good. So the interrupt to the classification to say, yeah, you've got a badge, drives more people away than you get by people who are motivated to get to the badge. So that means we did a bad job of gamifying. But then games are hard. And I think it's very difficult. I think it's hard to build a new
anyway. And there are lots of startups that testify to that. I think doing that with the constraints of, oh, and by the way, it's got to produce useful galaxy data is really tough. And you end up in this uncanny valley of educational games where a talking unicorn explains Newton's second law to you or whatever else. Maybe that was just me. And so you can go all the way. I think you could build an excellent game, fold it. You know, there are these examples out there that do complicated tasks through good gaming. But we're trying to stay on our side and say, look, this is real science. That's what people are motivated by. You do this not as an alternative to Angry Birds, but you do this because you want 3 to 5 minutes in your day in which you've done something useful. And I think mucking about with that by putting a leaderboard in and so on can have consequences that are much greater than just people clicking more. There's a longer version of that talk around, but that's where our thoughts are.
You did speak about experience and people discussing things, and there I would expect that that you track basic statistics like this. Every forum has like this person has posted so much, and he's created, he's liked by so many people. So you do stuff like that.
No, actually, we don't. Mostly because we built our own discussion environment and it's not hugely well developed, but also because the users didn't want to be identified by their classification count or their post count. So people don't want to wander around with a badge that says I've done 20,000 galaxies. That doesn't necessarily transfer to status in that community. We've been arguing about this, and we'll do some experiments. I think the stuff that works, incidentally, is not like gamified, but there's some papers in economics that have begun to talk about gameized behavior. So we do see the volunteers on the forum inventing games and using the site in a playful way. So on Galaxy Zoo, there was an organized search for an alphabet of galaxies. So in Snapshot Serengeti, there's a bunch of people who want to try and identify all 50 species and who keep track and award themselves points. But I think it's interesting that that works well when it comes from the community and not from us. And I think that distinction's really important. I think there's a lot more to be done in exploring that. But it's interesting, when I give this talk to web developers, they assume that we just haven't had the funding to do the gamified bit, because it's so ingrained in people that clearly you build everything as a game, and you have a badge and you have a leaderboard and so on. And I think we can show that you can do interesting stuff and build interesting communities without relying on that, if the basic motivation is strong enough. So I'm now having an argument with people who aren't in the room, but that's fine. Yeah.
You played around with and tested to adapt the pages to mobile devices and apps maybe. I mean, I'm thinking, if I'm at home, I might have things to do, but if I'm sitting on the tube or a bus or something, I'm feeling a bit bored getting there.
Yeah, playing around is right.
Do app for a while, and the average number of classifications on the app was more than 1,000 times larger than the web. And all right, that's partly self-selecting, so you have to download the thing, but nonetheless, it was actually built by a volunteer, and we've got a new Galaxy Zoo app that's coming out that's been volunteer built as well. I think it's hugely important. We've really struggled to get anyone to fund us to build apps of this. Funding agencies seem to have learnt the fact that everyone wanted to build an app and therefore all apps are bad. So the sites work quite well. The newer ones work quite well just in the browser on a mobile device. But I would love to be able to just have the Zooniverse app and to push tasks to people. I think one of the advantages of that will be when we get to this new telescope, I want to be able to identify the fact that this image that's just come in needs your help and be able to send you a push notification to say, actually, have you got 30 seconds? I think that will be a very powerful interaction, but we haven't really gone down that road yet.
Let the open source community do its thing.
Yes, so
And we're just rebuilding the software, which is all being rebuilt in the open, and will then be stable and will have documentation and so on. Yeah. We've also learned that we should have employed some more software developers early, right? We've gone from academics who know how to do software development quite well to just hiring, when we can, web developers. And so our practices are getting much more robust, and that means you can engage with the open source community, but in a much more formal kind of way. Mostly from the back of the sofa. No, we've been lucky. So the three major funders have been the National Science Foundation in the US, mostly through their computer science division. The Alfred P. Sloan Foundation in the States has been a big supporter, and the rebuild of the platform was being funded by Google as a digital global impact award. So that created, interestingly, that latter funding we were hugely grateful for, created an immediate conspiracy theory. So you can find there's a group of about 10 people on the web who are convinced that I secretly work for Google and that we're using their classifications for ill. But I assure you that's not true. Probably.